Okay, so we're going to look at chemistry test number 2 and just go through problems one at a time and emphasize on problem solving. So for question number 1, we are asked to find the basic anhydride formula of rubidium hydroxide. I want you to recall that the alkali metals, of course, hydrogen is in this column because of its electronics, not because it is an alkali metal. And just to encourage you to integrate more of the periodic table since it's not provided for you on your exam. We go from hydrogen to lithium to sodium to potassium to rubidium to cesium. And as we've previously discussed, these numbers change by 2, 8, 8, 18, 18. So rubidium is an alkali metal, and the formula of its hydroxide is simply RbOH. When I make an anhydride, I have to remove the elements of water. So I need 2 of these molecules, and they're really not molecules, they're ionic. So 2 of these formula units, and I'm simply going to remove the elements of water. So I'm going to lasso H2O. And what remains is RbO, Rb. Or Rb2O. Now this isn't covalent. I've made it look covalent, but that's just to emphasize what is left at this point. So the basic anhydride of rubidium hydroxide is Rb2O, and that is answer choice C. So the answer to question 1 is answer choice C. Let's move on to question number 2. What is formed when 2 amino acid molecules are linked by a reaction that splits out a water molecule? Well, an amino acid has the following general formula. You have an amine, and I'm not going to draw the physiologic charged amino acid, which is a zwitterion. You have a chiral carbon, you have a carboxylate. Again, it's usually negatively charged, and this is positively charged. You have an R group, and of course you have a hydrogen. What happens is if I take another one of these molecules, the R group can be something as simple as a hydrogen to something as complex as an indole functionality. But it's a dehydration reaction, just like reaction 1 was a dehydration reaction. I'm going to remove the elements of H2O. This is going to form an amide, and this amide functionality is better known in biology as a peptide bond. Now, I'm giving you a very minimal description of this. This is actually nucleophilic acyl substitution, where I make a carboxylic acid derivative, and in this case, the carboxylic acid derivative is an amide. In this case, we have a dipeptide. I'll call this one R1 and this one R2. So this is a peptide. Very stable functional group because it is the least reactive of all carboxylic acid derivatives. And peptide is credited response B on question number 2. Let's move on to question number 3. What is the maximum number of electrons possessed by an element in the third period? The answer to that is the recursive formula 2n squared, where n is the period. In this case, we're in the third period. So 3 squared is 9, and 9 times 2 is 18. Answer is 18. Now let's talk for just a minute about this, because there's some good chemistry in here that's being buried with just putting a formula. In the first row of the periodic table, all I have is a 1s orbital. I can have 2 electrons in the 1 orientation of the s orbital. Therefore, there's a maximum of 2 electrons. And if one were to look at the periodic table, one would realize that there are only 2 elements in the first row of the periodic table. Hydrogen, which is element number 1, and helium, which is element number 2. If I look at the second row of the periodic table, I can have a 2s orbital. And again, I can have 2 electrons per orientation. That's where the 2 in the 2n squared comes from. But I can also have a 2p orbital. And a p orbital has 3 orientations, x, y, and z. So the p orbital is shaped like a dumbbell. So that's the 2py. This is the 2pz. And you have another one that has a lobe that comes out straight at you, and one that goes straight away from you into the plane of the computer screen. So this is a 2py. This is a 2pz. This is a 2px. So I can have 6 electrons, 6 elements. 2 plus 6 is 8. The 8, and this will help us continue to master the periodic table. We have, actually I want to list this below so I can list all 8. So in the second row of the periodic table, we have lithium, we have beryllium, we have boron, we have carbon, we have nitrogen, we have oxygen, we have fluorine, we have neon. And if you count these, we have 1, 2, 3, 4, 5, 6, 7, 8. In the third row of the periodic table, even though we do not have filled d orbitals, we have the potential for 3s, 3p, and 3d. That's 2 times 1 plus 2 times 3 plus 2 times 5. 2 plus 6 plus 10 is equal to 18. If I start counting up the number of orientations, there will be n squared. For example, in the first one, there's only 1 orientation, or 1 squared. In n equals 2, there are 4 orientations, or 2 squared. In the third, there are 9 orientations, or 3 squared. This is how we get the recursive formula for the max number of electrons is 2 n squared. And I only realize this maximum number if the spins in each orientation are opposite. Spin up, spin down, plus 1/2, minus 1/2. All right, let's move to question number 4. Compound is formed when 6 grams of element A. Element A has a molar mass of 24 grams per mole. Reacts with 15 grams of element B, and element B has a molar mass of 20 grams per mole. What is the empirical formula for the resulting compound? So what I'm going to do with this one is I'm going to put the answer choices to the right. A is A2, B5, B is A3B, C is AB2, D is AB3. In terms of a strategy, it's a two-pronged strategy. Number one, let's find the moles of A and the moles of B. 2, let's divide by the lowest number of moles. This doesn't ensure that we'll be finished, but in most cases, we're going to be able to find the empirical formula fairly easily. So we have 6 grams of A, and the mass is 24 grams per mole. That means we have 0.25 moles. To show that formally, I have 6 grams of A, and I have 1 mole of A for every 24 grams of A. 6 over 24 is 1/4, which is 0.25 moles of A. We are going to use the same logic for B. 15 grams of B. I have 1 mole of B for every 20 grams of B. 15 over 20 is 3/4. That's going to be 0.75 moles of B. So we see a 3-to-1 ratio, so right away I know that A and C are not going to work. I'm going to divide both A and B by 0.25. That'll give me 1A, and that will give me 3B. That is answer choice D. D is the credited response for question number 4. Let's move on to question 5. I have a 0.1 molal solution of NaCl. And it has a higher boiling point than a 0.1 molal solution of glucose. And I need to rationalize why this data is the way that it is. This is a simple colligative property question. The 0.1 molal solution of NaCl is actually 0.2 molal of particles, because I have 2 particles for every formula unit. Glucose is covalent. It does not ionize, so it is essentially 0.1 particles. Simply put, the 0.1 molal solution of NaCl has a greater concentration of particles than does the 0.1 molal solution of glucose. The more particles you have, the more you strengthen the IMF. And the more IMF you have, the more energy you need to create a vapor pressure that can equal the external pressure, and so the boiling point increases. So I would have a depressed vapor pressure, a depressed freezing point, an increased osmotic pressure, and an increased boiling point for NaCl because I have a greater concentration of particles. Let's look at the answer choices. A reads, NaCl is an electrolyte and hence yields more molecules in solution. I like that answer. I do not like the word molecules. They're not molecules. They're ions. So clearly the author of this question is a little confused. Maybe he's or she's just a little too old for the business and they should retire. B, glucose is larger molecular weight. It has absolutely nothing to do with it. Eliminate B. Glucose is a hydrogen bonder, whereas NaCl is not. It doesn't depend on IMF. Eliminate C. D, NaCl is a hydrogen bonder, whereas glucose is not. That's a false statement. We're going to call statements like this S, B, S, because it is scientific bullshit. Never pick a response that's SBS. The best answer, even though it's flawed because Na plus is not a molecule and Cl minus is not a molecule, they are ions, A remains the best response to question number 5. That's nice. Okay, so let's look at question 6. We have 120 grams of NaOH. We dissolve it in enough water to make 20 liters of solution, and we simply want to calculate the molarity. Remember, molarity is moles of solute divided by liters of solution. We already know our denominator is going to be 2 liters. So we simply need to convert 120 grams into moles. The molecular weight of NaOH is 40. So we're going to have 3 moles. 3 moles divided by 2 liters is 1.5 molar. And that is answer choice B for question 6. The credited response is answer choice B. Number 7. Which of the following excitations, those are going to be promotions of electrons, would require the greatest amount of energy? So for A, we're going from 2s to 2p. For B, we're going from 1s to 3p. For C, we're going from 3s to 3d. And for D, we're going from 2s to 3s. You know, this question is very straightforward. Within a principal quantum number, the energy gaps are going to be much, much smaller than when I go from one principal energy level to another. So the 2s to 2p and the 3s to 3d, they're not going to be very much. I'm going from principal energy level 1 to 3 in B, and I'm going from 2 to 3 in D. B is definitely going to be the greatest energy. It must absorb a greater amount of energy to go from 1s to 3p than in any of the other answer choices. And so for number 7, the credited response is B. Number 8. Which of the following radiations would be attracted to a positively charged electrode? Answer choice A, we have a neutron. A neutron has no charge. So I would throw that one away immediately. B, a gamma particle. Again, no charge. An alpha particle is a doubly ionized helium nucleus. It's positively charged, and it's going to be repelled. So A and B are neutral. C is positively charged. D, a beta particle, is nothing but an electron. An electron is a beta particle. D is the credited response for question number 8. All right, so question number 9, we're given a potential energy diagram that is labeled for you. So we have the energy of the reactants is at minus 12 kJ. Energy of the products is minus 17 kJ. The energy of the transition state is minus 7 kJ. And we are asked, what is the activation energy for the reaction, for the forward reaction? Actually, the question doesn't distinguish between the forward reaction and the reverse reaction. And that is a big, big no-no in this question. So we're going to assume they're looking for the forward reaction. And so when we go from negative 12 to negative 7, the activation energy is always going to be positive for chemical transformations. And that's going to be 5 kJ. 5 kJ is answer choice C for number 9. Now 10, actually I take that back. No, 10 and 11 are linked to this diagram, so I want to go ahead and discuss those quickly. Number 10 asks us about the above reaction. So the energy that is plotted on this axis is G. And notice that it is exergonic, which means it's spontaneous. And so we can eliminate D. Now, the reaction goes from negative 12 to negative 17, so it liberates 5 kJ of energy. So that makes the best answer for number 10, answer choice B. So A reads it's spontaneous and it liberates 17. That's not correct. B reads it's spontaneous, it liberates 5. That is correct. C reads it's spontaneous, it liberates 10. That is incorrect. D reads it's non-spontaneous. That's incorrect. So for number 10, the credited answer is B. Finally, number 11. If the energy of the transition state were lowered from negative 7 to negative 9, the reaction would, quite simply, this is what an enzyme does. It lowers the energy of activation. It would occur more quickly. So it would be faster, making the best answer choice D. I'm going to stop this particular video, so we'll pick up with the next one on question 12 on chemistry exam number 2.